Today is my birthday, so I decided to show you all one of my favorite proofs of all times. It is a proof of Fermat's little theorem, which is not to be mixed up with Fermat's last theorem, which basically says that a to the power n plus b to the power n equals c to the power n has no integer solutions for n greater than 2. It's quite a well-known theorem because Fermat basically trolled the whole math community for 350 years by saying that, I know the proof, I have the proof, just that I don't have enough space to write my proof. And then it took us 350 years until Mr. Andrew Wiles came up with the proof of it. So its lesser known little brother, Fermat's little theorem, tells a different story. It says that for any prime number p and a positive integer a to the power p minus a is congruent to 0 mod p. In which I'm basically saying that if you take some positive number a and you raise it to some prime number p, then a to the power p minus a is something that is divisible by p. Usually I wouldn't really make this video because I myself came across this proof from a methodology video, so there are already videos out there on this exact same thing on YouTube. But since it's cake day, I thought, why not make a little exception.
Y me llama el cocinero. Risita, ¿qué? Ve por la paellera. Venga, que las 2 de la tarde ya están aquí. Miren, bañador. En las chanclas. Todo despeinado porque no me dio tiempo nada ponerme las chanclas y el bañador. Voy a la playa, había subido la marea. Eso. Tú, había subido la marea y encontré una paella.
So the proof actually uses combinatorics, and that's where you can tell it will be a sexy proof. And when we see a to the power p, we can see somehow that combinatorics might come in handy. So for the proof, what I will be doing is I will literally be making necklaces, and I will be making necklaces such that, actually, let me choose something that is solid. Let me choose the prime number 5 and the positive number 4. And you can see along the way how it will generalize to any positive number a and prime b. And what I will do is I will take p number of beads, so 1 2 3 4 5 beads, and of course they're in a circular loop, so it makes a necklace. And what I'm doing is that I have at my hand 4 colors, and I'm making different colored necklaces. So maybe let's say my the colors that I have are red, blue, sorry, this is not red, blue, green, and let's say yellow. So one combination I can make, let's say this is red, and then I can say green, and then let's say these two are blue, right? So I don't have to use all the colors, that's up to me. And then once I do this, what I will do is that I will cut the necklace from different points such that I get a different sequence. So for example, if I cut this from position number 1, I get the sequence red, green, blue, blue, blue. So this is the first sequence. If I cut it from here, I get red, green, blue, 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 red. And just to show you more clearly, if I cut it from point number 3, it will be green, blue, blue, red. So you can see that there's a certain sort of shift that's going on here. And the reason when I cut these from different points, and actually there'll be 5 different points because there are 5 beads, so here'll be point number 4, point number 5. Now I am sure that when I cut it from different points, I will get a different sequence. And the reason behind that is that we're basically using the fact that prime numbers are not so nice numbers. They're not divisible by anything else. So you cannot group these into any other bunch of numbers. So because they're so unsymmetrical, I can be sure that there won't ever be in this particular one, I will get 5 different sequences. So if I took something which was not a prime number, let's say 6, 1 2 3 1 2 3 4, let's just add 1 here. Now it is not always true, it is not always necessary rather, that if I cut from here and if I cut from here, it will be the same. And the reason behind this is that because of the symmetry, that it is possible that when I cut from these 2 points, this, yeah, actually use this sequence may be equal to this sequence. So here we're essentially using the fact that they're prime numbers. We're bringing in the prime number property. Now, one thing to note here is that if I take this same sort of necklace and I rotate it 1, 2, 3, 4, 5, I rotate it such that I bring about, let's say, one change, one beat change. So this will be red, red, green, blue, blue. So I have rotated this in this direction. Now, I'm not doing this because when I cut this from different points, I get the same thing back. So I won't be rotating the same necklace because because it will result in the necklace that I rotated. I'm only concerned in the different combinations of colors that I can make. One more thing that I can add here is that given all the different combinations I can make, one thing that I do not want is that I do not want all the colors in my necklace to be of the same, all the beads in my necklace to be of the same color. So let's say red, 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 red. I do not want this. That would be a boring necklace. Now essentially what I will do is I will count how many of these sequences there will be. And so it is easy to see that at every point there are 4 choices that I can make. So there are 4 to the power 5 combinations of these. And now I need to account for the fact that I won't be making these boring one colored necklaces. And since there are 4 colors, there will be 4 boring necklaces. And so 4 to the power 5 minus 4 represents all these sequences of different necklaces that I can make, differently colored necklaces that I can make. And so since for every necklace there will be 5 color sequences because I can cut from 5 places, if I divide this by 5, this will give me the number of differently colored necklaces that I can make. And so I know that the number of necklaces that I can make is an integer. I can be sure that this will also be an integer. So essentially, if we generalize this, we get that for any A colors and P beads, A to the P, where P is prime, of course, and the reason why it must be prime is because for a number that is not prime, there can occur symmetries. And since there can occur symmetries, it is possible that there are not exactly P different sequences of colors. There can be an overlap. So A to the power P then minus A over P basically gives you the number of necklaces that there can be given A colors and P beads. And since that is an integer, this must also be an integer, and this is our proof of Fermat's little theorem. So, I think it's a pretty neat little proof. And of course, now that I look at it, it doesn't seem that good because I've looked at it so many times. But the first time that I came across it, it felt really good. So anyways, this was the whole proof. Hope you liked it. QED. See you in the next video.